Hello everyone, my name is Jiang Zhenyu from Tongji University. My topic is efficient architecture for convolution and software mass function in deep learning accelerator. The content mainly consists of the following sessions: introductions, hardware architecture of the system, hardware optimization of accelerator, experimental resource, conclusion and discussion. Convolutional neural networks (CNN) outperforms traditional machine learning algorithms across a wide range of applications, such as object recognition, image segmentation, and autonomous driving. However, their ever-growing computational complexity makes it necessary to design efficient hardware accelerators. CNN generally consists of convolution and ReLU layers, multiple convolution layers, and pooling layers, and a fully connected layer and an output layer. The convolution layer is to extract the feature information from the input feature map. Activation layer is an activation function that decides the final value of a neural. Value function is the most widely used activation functions. It effectively removes negative values from an activation map by setting them to 0. Pooling layers reduce the dimensions of the data. Finally, after several convolutional and mass pooling layers, the high-level reasoning in the neural networks is done via full connected layers. Networks in a fully connected layer have connections to all activations in the previous layers. As we can see in the picture, their activations can thus be computed as an affine transformation with matrix multiplication followed by a wires offset. The software mass function is a generalization of the logistic function to multiply diversions. And this shows the architecture of the DLA. First, we need to configure the configuration register, such as weight size, weight curves, map size, channels, or operation modes. The input interface and output interface communicate with the processor via the XI bytes by DNA. At the preprocessed layer, we know great preprocessing of the matrix is performed, as well as the floating point to fixed point conversion. After padding and rearranging, data will be sent to the MAC array to complete the convolution operation. After pooling and convolution, data will be sent to the fully connecting layers, and the final results will be transferred through the outer interface to SRAM. Because of the complex matrix calculation in the convolution and the expensive exponentiation and the division calculations in softmax function is necessary to design efficient hardware architectures for these two functions. Let's first take the 1D convolution as an example. Input matrix D and the convolution curve is G. The convolution can be written as the following matrix multiplication form. And the result needs 6 multiplications and 4 additions. Then we can transfer the calculation to this form. The process can be expressed by this equation. We can see the results only require 4 multiplications and 12 additions. Since multiplication is much more complex than addition, so the total complexity can be reduced. Let's see the 2D convolution. Input matrix is K and the curve is W. The matrix multiplication is this form. And we can divide the large matrix into smaller submatrices. Then we can get this. And each submatrix can also be transformed by these equations. So finally we can get this. The final result becomes 4 submatrix multiplication, and each matrix, as we can see in the 1D convolution, needs 4 multiplications. So it needs totally 16 multiplications, which greatly reduce the multiplication times. Mac array is used to perform convolution operations. Each Mac cell has the same size and same function. We can see each contains 4 PE, and each PE performs 1 Mac. The Mac arrays is as this form. Takes advantage of the regularity and parallelism. So the architecture is more regular and is easier to route for back-end design, thus greatly increasing the frequency. After convolutions, pooling, and activation, the final layer of deep neural networks is usually a fully connecting layer with softmax function. As we can see in this equation, fxi equal to exi divided by the sum of exj. The exponentiation and the division calculations is used. It's very complex to implement these two functions. And we can see the direct calculation hardware architecture is like this. Then we can transfer the equation to this form. The numerator and denominator both divided by EX mass, so that EXI minus EX mass is less than or equal to 1. And the division is converting to subtraction as well as logarithmic operation and prevents overflow. The subtractors and log units has lower complexity. The hardware architecture of Softmax function can be shown in the figure. Since the critical paths of log unit and subtractors are shorter than divisors, the critical delays can be significantly shortened. So then the sorting units aims to find out the maximum value of xi. It contains multi-level comparator trees. The asp unit, the power of E can be transferred into such form. The power of E is expressed by the power of 2. And since we can set the integral part is U and the decimal part is V, then F equal to this part, this form. And the power of 2 can be easily implemented in hardware. We just need to shift 2 by U base. And also, minus V to the power of 2 can be expressed by a linear function kV plus B. So the final architecture is like this. X multiplied with log 2e. Since log 2e is a constant, so the multiplication can be a constant multiplication. The next is log part. We can set the sum of EXI minus EX mass to be S. Then we set M greater than 1 and less or equal to 2. And N is a non-negative integer. Then we can express S by this equation. S equal to M multiply the nth power of 2. So the log S equal to log 2n plus log M equal to log 2 multiply with the sum of n plus log 2m. And since m is greater than 1 and less than 2, so we can express the log 2m equal to m minus 1. then the equation can be written as this. All we need to know is m and n. The n can be expressed by y minus z. The y is the first one of s, the position of the first one bit of s, and z is the decimal point position, and m is s shifted right by n bits. So then we can get log s. Here are the results. We use Design Compiler 2016, TSMC 28 nanometers, HPC plus. The working condition is SS Global 125. The voltage is 0.81 volt. As we can see, the area and cell count, as well as path length, are greatly reduced. And here are the simulation waveform. We use the two model themes. Here are the conclusions. CNN are widely used, but the hardware cost is expensive. Significant hardware efficient improvement can be seen by the proper convolution and Softmax function. And what we will do in the future is focus on the sparse matrix operation optimization and to reduce memory storage and data bandwidth. And we need to do low power design. That's all. Thank you.
Hello everyone, my name is Liu Runzi. I'm from Xi'an University of Architecture and Technology. Today, I will do a presentation titled Two-Stage Task Planning Based on Resource Interchange in Space Information Networks. In this talk, I will first give the background of our research. Then I will present our system model. Next, we formulate the task planning problem and decompose it into two stages. Afterwards, algorithms are designed for each stage, and finally, simulation results are presented. Now, let's first look at the background of this work. Space Information Network is a network system which could acquire, deliver, and process spatial information in real time. Due to the features such as wide coverage and flexible networking free from geographical restrictions, space information networks have played important roles in both military and civilization fields. However, SIN also has some challenges. For example, due to the high-speed movement of space nodes, the distribution of resources of SIN is dynamic and non-uniform in both space and time dimension. Moreover, the space-time distribution of task levels is also of great randomness. Then, with the increasing task demands, the temporal shortage of some resources in certain regions become more and more obvious. Faced up with these challenges, some intrinsic properties of SIN, such as resource mobility and emerging technologies such as software-defined payloads, are utilized to compensate the bottleneck resource timely. Some existing works study the mode of utilizing resource mobility and shows that utilizing resource mobility can effectively improve the service capability of SINs. Another existing work proposes a task planning strategy which considering the interchange of storage and communication resources of SINs. Another work utilizes graph model to characterize the transformation among network resource functions and proposes a resource management methods. All those above methods have good performance in terms of compensating the bottleneck resources. There still exists a lot of room for improvement. For example, these methods only exploit resource mobility qualitatively, while the quantitative study of utilizing conditions is still lacking. Moreover, in spite of enhancing the flexibility of the matching between resource combinations and tasks, the utilization of resource interchange also increases the space of feasible solution, which causes huge computation complexity. To this end, in this paper, we aim to propose a two-stage task planning strategy based on resource interchange. We first develop a graph model to capture the dynamic coordination relationship among resources in SIN. Then we explore the mechanism of resource interchange and propose its quantitative condition. Afterwards, we formulate the task planning problem and decompose it into two stages, then design algorithms for them. Finally, simulation results show the effectiveness of the algorithms. Let's look at the system model. We consider SIN, which consists of some observation satellites, data relay satellites, ground stations, a data processing center, and some observation targets on the surface of Earth. Moreover, there are also some observation tasks which can be depicted by the observation target and the amount of data required to be acquired, and the earliest start time and latest end time of the task. In order to utilize the resource interchange, we consider the time-varying resource graph model, which can not only jointly represent the multiple kinds of resource or SRN, but also take resource mobility into account. To construct the TVRJ or SRN, we need first to divide the planning horizon into k equivalence time slots. Then the time-varying resource graph is a k-layer direct graph, wherein each layer represents the topology of SRN or corresponding time slot. And the vertex in TVRJ represents the nodes in SRA for each slot, and the arcs in TVRJ represent the different types of resources in the network. There are three kinds of arcs, which are observation arcs, storage arcs, and transformation arcs, which represent the observation, storage, and transmission resource in SIN respectively. In SINs, the bottleneck resources can be compensated by the transformation or replacement with non-scale resources, which is referred to as the resource interchange. Resource mobility improves the freedom of coordination relationship between different resources, thereby bringing additional opportunities for different resources to replace each other to complete our tasks. Taking this figure as an example, satellite 2 acquires data from the observation target and need to transmit this data back to the ground. However, relay satellite is occupied by satellite 1. So satellite 2 stores the data in its memory and fly along its orbit until it is above a ground station, and then the data can be downloaded, thereby realizing the exchange of storage resources and communication resources. As the same resource service capability is the essential condition for different resources to interchange with each other. Here we define two metrics to uniformly quantify the service capability of resource combinations in SINs. The first metric is the spatial displacement, which is a vector representing their position difference. The second metric is transferred data volume, which is the amount of the data the resource can handle in a slot. Then the service capability of a resource is defined as the product of these two metrics. With the TVRJ, the task execution process can be modeled as follows. Moreover, the task planning problem can be modeled into multi-commodity flow problem in TVRJ, which can be formulated into an optimization problem. As we can see, the objective of P1 is to maximize the number of tasks that can be successfully executed. And for the constraints of P1, the constraint 1 specifies the amount of data that should be delivered for each successfully planned task. Constraint 2 is the flow conversation constraint, Constraints 3 and 4 are capacity constraints of the arts. Constraints 5 to 8 are conflict-free constraints for the observation or transmission resources, which can only service one task at each slot. As we can see, P1 is a maxed integer linear programming problem, which is a NP-hard problem. Moreover, we can find that the complexity of solving P1 mainly comes from the large number of feasible resource combinations. Furthermore, the conflict relationship among resources has correlation in time dimension, so it is inefficient to directly search the optimization task plan from all the feasible resource combinations. To reduce the complexity of solving problem P1, we explore the correlation among resource combinations and divide the solving process into two stages. The first stage is coarse-grained global planning. Its main idea is to sample the feasible resource combinations and obtain a candidate resource combination set, and then the optimal task plan can be searched from this set, thereby reduce the complexity of global optimization. The second stage is fine-grained local adjustment, which aims to adjusting the global planning results locally by utilizing resource interchange so that more tasks can be successfully planned. Hereinafter, the algorithm designed for the two stages will be introduced in detail. The coarse-grained global planning is composed of three steps. In the first step, we sample the feasible resource combinations of each task and obtain a resource combination candidate set, denoted by PE. Then, the aim of global planning becomes to match the task requests with a set of conflict-free resource combinations in PSE to maximize the number of successfully planned tasks. Then, in the second step, we construct a resource combination conflict graph to represent the conflict among resource combinations. Then the problem is transferred into a maximum independent set problem of RCJ. Therefore, in the third step, we search the optimal task plan from the candidate resource combination set based on the resource combination conflict graph. Specifically, we base on the largest degree first rule for the maximum independent set problem. A global optimization algorithm based on candidate resource combination is designed. Here is a flow chart of this algorithm. After the global planning stage, we adjust the resource allocation result locally through the resource interchange to make more tasks successfully planned. The main idea is, firstly, we quantify the resource shortage degree of the unplanned tasks. Then, we adjust the local resource allocation of already planned tasks to resource to release the occupied resources for the unplanned task by resource interchange. At last, we allocate resource combinations for the unplanned tasks to make more tasks being successfully planned. In the simulation part, we conduct a simulation scenario of SRN based on STK software. The parameters of the scenario are shown in this table. Moreover, we conduct two algorithms for comparison, which are time-oriented decomposition based on task planning algorithm and resource-oriented decomposition based task planning algorithm. Figure 4 and Figure 5 shows the number of completed tasks and the average working time of the imagers for the three algorithms with varying task requests. It can be observed that in both figures, the proposed RITPA algorithm performed better than the existing works. Figure 6 compares the computational time of the three algorithms with varying task requests. It can be observed that the TD-TPA requires the latest computational time, and followed by RITPA, and RDTPA requires the most computational time. This is because RITPA proposed in this work simples the feasible resource combinations in the global planning stages, thereby striking a good balance between the performance and the computational capacity. That's all on my presentation. Thank you.
Hello everyone, glad to be here and participate the EAI Chinacom 2020. and it's my pleasure to give a presentation about our research. Our research topic would be low latency wireless communication system implemented on a software-defined radio platform, and it's mainly about our system design to achieving low latency in cellular network. My presentation mainly consists of 5 parts. First, an introduction about the research background. Then, we analyzed the composition of cellular network latency. And third, we will show the system design and deployment of our prototype low latency platform. And then, we will give some experimental results and test data about the performance. Finally, reach the conclusion and discussions. The 5G wireless communication has been developing rapidly in recent years and is also being commercialized worldwide. One big difference between 5G and 4G is that 5G is expected to support multiple new applications and use cases rather than traditional communication scenarios. So 3 different service categories have been introduced: enhanced mobile broadband, the EMBB, ultra-reliable and low-latency communications, the URLLC, and massive machine-type communications, MMTC. The initial phase of 5G development is EMBB, which provides higher throughput and data rate with moderate latency. High-resolution video streaming is the main application scenario of EMBB, such as AR, VR, MR, or UHD and panoramic video, etc. With the development of other technologies and industries, latency is becoming a more and more important performance indicator other than data throughput. So URLLC is proposed to meet the requirement. It is officially supported in NR Release 15 and Release 16 by 3GPP specifications. The figure on the right shows some different use cases and their requirements of latency and the packet error rate. Many new applications such as factory automation, autopilot vehicles, tactile internet, they all have stringent latency requirements to ensure the safety and real-time performance. There are several key enablers to achieve the latency requirement, such as short TTI, grunt-free scheduling, the NORMA, overlapping and preemption, caching, the edge computing technologies such as MEC, fog and mist, and network slicing. These enabler technologies optimize the latency at different layers of network stack. According to our survey, many researchers have done some related works, but most are evaluated by simulations. So we come up with the idea to implement a low-latency communication network on a realistic software-defined radio system to evaluate the performance. In our research, we choose scheduling scheme and TTI as 2 critical points to optimize the latency. Scheduling is a key feature of MAC layer. In the radio access network, the base station acts as the central control entity to allocate time and frequency domain resources and coordinate all the UEs attaching to this base station by signaling on control channels. So different scheduling schemes may have different impact on transmission latency. Dynamic scheduling is the default in traditional LTE system. It needs 2 round trips to finish one transmission. The first round is the scheduling request and grant procedure, and the second round is data and acknowledgement. The signaling procedure of request and grant increases the latency, and there will be even more overhead when transmitting large amounts of small-size packet. So dynamic scheduling scheme is fit for mobile broadband traffic with no strict requirements on latency. And then let us look at semi-persistent scheduling. Figure shows that when SPS is applied, the request and grant signaling procedure is performed only once at the first attempt of transmission, and afterwards, the uplink data can be sent on pre-allocated radio resource without performing the scheduling procedure again. The radio resource is allocated in a periodic manner, and the period of SPS can be configured by the base station through RRC signaling. The user equipment would wait for its turn to transmit uplink data. So SPS is suitable to transmit periodic data, such as VoIP traffic and sensor network data. So next, let's look at another factor that may impact latency, named transmission time interval, the TTI. It is the basic time unit and decides the time granularity for many procedures in network stack. TTI is mainly decided by the design of frame structure. In 4G LTE, TTI is fixed to 1 millisecond due to the static frame structure, which is equal to the duration of one subframe. In 5G NR, numerology is introduced to adjust frame structure dynamically. So numerologies represents different configurations of subcarrier spacing, the SCS. According to the theory of OFDM, the OFDM symbol duration need to be inversely proportional to the SCS to maintain the orthogonality of adjacent subcarriers. This gives a possibility to shorten the duration of TTI. The baseline configuration of 5G SCS is 15 kHz and can be scaled with a factor of 2 to the power of mu, where mu can ranges from 0 to 5. The table below shows some combinations of numerology, SCS, the OFDM symbol duration, and TTI. When numerology increases, the frame structure is expanded in frequency domain and is compressed in time domain. Figure shows the comparison of different numerologies. Increasing numerology to get a shorter TTI can have better performance on latency, but would also have side effects such as higher intersymbol interference, the ISI, and lower efficiency of spectrum utilization, and weak against multipath channel because of a shorter cyclic prefix. So a trade-off should be made between latency, spectral efficiency, and robustness to choose a suitable TTI to meet the requirement of particular applications. And in our experiment, we tested the performance of 1 millisecond and 0.5 millisecond TTI. And then let me introduce the system design and deployment. We use software-defined radio technologies to set up our network platform. SDR is a kind of radio communication system which implements the radio signal processing by software instead of specific hardware. It gives more flexibility and convenience and is very suitable for implementing prototype system. Our peripheral radio device is built up with a Xilinx Vertex 6 FPGA evaluation board and analog device AD9361 radio transceivers, and use PCIe interface to stream samples to the host machine. The SDR software we use in our system is Open Air Interface, the OAI. It is an open-source software radio framework initiated by the Eurocom, which implements full protocol stack of user equipment, base station, and core network, making a complete cellular network system. Because the 5G NR version of OAI is still under development, so we use the 4G LTE version of OAI as software framework to make our optimizations. And the 3 host machines are needed to deploy our SDR system. Host machine 1 runs the components of LTE EPC. Host machine 2 and 3 are plugged with peripheral radio device and run the soft modem program of eNode B and UE respectively. and host machine 1 and 2, they are connected to the same router to provide a backhaul link. To achieve semi-persistent scheduling, so first we disabled the uplink scheduling request and grant procedure. Then we use subframe number as index to allocate uplink resource to UE to implement the behavior of SPS. So we also set different period of SPS. For example, if period is set to 1, data can be transmitted on every TTI. And if period is set to 3, there is only one transmitting TTI in every 3 TTIs, just like the figure above shows, and the green blocks indicate the RB scheduled by SPS. And next, we try to adjust the duration of TTI. Because the LTE version of OAI doesn't support adjustable subcarrier spacing in software, so we need to set it manually by configuring the bandwidth, the sample rate, and other parameters on radio device, and let both UE and eNode be running on 15 kHz or 30 kHz subcarrier spacing, so that making the system running at 1 millisecond or 0.5 millisecond TTI respectively, as shown in the figure below. So here comes the experimental results. First of all, we validate the performance of short TTI. So solid lines are 1 millisecond TTI and dashed lines are 0.5 millisecond TTI. From the figure, we can find that there is a proportional relation between TTI and latency. So when TTI is shortened from 1 millisecond to 0.5 millisecond, the ping latency almost cut in half. So it's a significant improvement. And we also tried to shorten the TTI further to 0.25 millisecond. I means the expanding the subcarrier to 60 kilohertz. But UE failed to complete the random access procedures and couldn't attach to the base station. And this may be caused by the increasing ISI and the limitation of hardware's capability. And secondly, we validate the performance of semi-persistent scheduling scheme. From the figure, we can find that 1 millisecond period SPS can reduce the latency by about 4 to 7 milliseconds, comparing with the baseline when transmitting different size of packet. And this is mostly contributed by saving the overhead of request and grant procedure. We also find that packet size is another factor that may impact the network latency. In our experiments, we fixed the transport block size to 101 bytes. So if the uplink packet size is small enough to be sent in one transmission, SPS could have a better latency performance. But if packet size is as large as several times of TBS, SPS performance may be worse than dynamic scheduling. So these experiments proved that SPS is fit for periodic small packet traffic. So setting the uplink SPS period to 1 TTI would have the best latency performance because all the uplink data packets could be transmitted immediately, but at the cost of a lower spectral efficiency and resource utilization. And the ping round-trip time of baseline dynamic scheduling is about 15 milliseconds when transmitting 64 bytes ping packet. And by combining shortened TTI and semi-persistent scheduling together, so we achieved a minimum of 5.3 milliseconds. With this latency level, we have reduced about 65% of the ping latency comparing with the LTE baseline profile. So in our work, we analyzed two major factors contributing to network latency in wireless system: scheduling scheme and TTI. And we implemented semi-persistent scheduling and short TTI schemes on a software-defined radio platform and verified the performance. The experimental results shows a notable improvement on network latency and can be reduced significantly comparing with the baseline LTE system, so making it feasible to deploy latency-sensitive applications. As part of our future work, we also investigate other methods to reduce wireless network latency, such as mini-slot frame structure and HARQ RTT shortening. So by exploiting the potential of all these methods, we expected to reduce the latency furthermore and build up a practical system that can meet the strict latency requirements of ULLC. So we are also considering using this platform to deploy some latency-sensitive applications. And here are some of the references. And thanks for listening.
Hello everyone, my name is Pan Pingping. Today my report topic is a deep learning compiler for vector processor. I'll start with some background and work on the compilers, then focus on front-to-back optimization and code generation, and finally the evaluation experiment and summary. The first part mainly includes three aspects. The first is the overview, and the second is about the research status at home and abroad. The third is about the switch vector DSP processor architecture. Deep learning compiler serves primarily as a bridge between the top framework and the target device. Trained models can generate optimized operator and interface code for different target platforms through deep learning compilers to realize the deployment of multiple target platforms for a single model. I present a deep learning compiler for Swift DSP based on LLVM framework, which called DLCS, and allows DL models to an intermediate representation of two levels. The high-level IR realizes target independence optimization, including kernel fusion, data replacement, and data simplification, where the low-level IR allows the compilers to perform target-dependent optimization, such as add slot with very long instruction word and intrinsic function of single instruction multi-date instruction. Compilers have a long history of development, and the more symbolic events are the emergence of YACC and LEX, which represents the key technologies of the traditional compiler front-end, such as lexical analysis, syntactical analysis, and semantic analysis. And the key technologies of the back-end are instruction selection and scheduling, register allocation, code emittings, and so on. Some of the mainstream compiler frameworks are GCC, TVM, XLA, DLVM, and so on. The target hardware supported by DLCS is Swift DSP. On the one hand, Swift DSP has its own high-performance instruction set. On the other hand, it has a complex chain. In addition, it supports VLIW, SIMD, software pipeline, hardware loop, and so on. The second part mainly includes three aspects. The first is about model tailoring and model representation. The second is about optimization of the calculation diagrams. The third is about support the intrinsic functions with SIMD instructions. I used the multi-step iterative algorithm to clip the channels at each layer, selected the input channels to be clipped and reconstructed errors with the least squares methods by LASSO, and finally fine-tuned the model. There are three main forms of multi-level compilation representation of neural network model. The forms of pre-processing networks IR is about FSM plus text structures. The forms of high-level IRs is calculation diagrams. The forms of low-level IRs is about LLVM IR. Data simplification merely includes knot pruning and constant folding. Knot pruning is the removal of identity knots associated with the training phase during the deployment phase, which simplifies the calculation diagrams and service operating cost. Custom for this optimization is to replace the output values in the calculated graph with norms that can be determined in advance by a constant. The data layout transformation optimization merely refers to the storage mode of transformation tensors to adapted to the target hardware architectures. The data layout optimizations performed by DLCS is to convert various data layouts such as NHWC and CHWN into NCHW format, where N represents the number of images in a batch, H represents the vertical height of the number of pixels in the director, W represents the width of the number of pixels in the horizontal direction, and C represents the number of channels. Operator fusions is easier to understand, like polynomials into equations. Data replacement replaces serialized data by placing the flag information in the unsigned child arrays, which is finally found in the result files and replaced with the original binary serialized data. There are three formats of SIMD instructions in Swift architecture. Their corresponding data types in the front and back end files are shown in the table below. First, I used the attribute and inline mechanism in source level Swift vector.h to define vector types, attributes, and encapsulate intrinsic functions. Then I do a one-to-one mapping of the intrinsic functions on the front end and the built-in functions on the middle end. Finally, do the relationship bindings for the intrinsic functions at the back end and the built-in functions at the middle end. The third part merely includes two aspects. First is about the S.VLIW emissions. The second is about the software pipeline algorithm based on Swift architecture. As for the S.VLIW emitting algorithms, I will first introduce its corresponding hardware constructs. First, it is the instruction format constructs as shown in the figures on the right, where the instruction format of the 4-register and 3-register types is listed. Next, it's about 2-register instruction and 1 register with 1 intermediate number instruction. Finally, there is an intermediate number instruction and 1 register instruction. In addition, hardware constructs include instruction store constructs and single store packaging constructs. The former is shown in the figure on the right, which specifies the allocation of slots for on instructions. The latter specifies that certain expansion instructions must occupy a single VLIW packet. I used the DFA to package the A.VLIW. The figure on the right shows an NFA of the 2-slot data transfer diagrams, which was converted to DFA through the algorithm of compilation principle. And this is a simplified diagram of the DFA for A-slot state transmission, where state 0 is the start node and the state 11 is the end node. The entire S.VLIW packaging algorithm process is shown in the figure on the right. The code steps are the DFA detentions described earlier and the data dependence checking. The final S.VLIW coding algorithm adopts greedy algorithm. The lessens the number of allocated dots and the more or the positions of the allocated dots are in the front, the more they are allocated first. Data flow diagrams acquisition is the first step of software pipeline. The importance of data flow graph lies in obtaining the detection of the critical register path and delete slot insertion. The second step is the calculation of some importance parameters as shown in the figures on the right, where the height of instruction represents the maximal numbers of instruction successors. Instruction depth represents the delay of instruction on the register critical path. Mo represents the flexibilities of instruction in scheduling algorithms. ALAP stands for which circles the instruction can be placed at the latest. ASAP represents the earliest circles in which instructions can be placed. MII refers to the number of stand-up interval cycles between two consecutive iterations in software pipelinking, and the MII is divided into resource-limited minimal stand-up intervals and data-dependent minimal stand-up interval. The figure on the right is the corresponding parameter values of the data flow diagrams introduced earlier. Cyclic factor expansion optimization merely retracts various vectors such as upper and lower limit factor, minimal cycle target factor, branch pressure factor, data-dependent pressure factor, and register allocation pressure factor. The decisions and optimizations of node priority lies in taking into account the instruction set characteristics of Swift architectures and splitting the priorities proportions originally divided into half of MUS and MII into the optimal proportions as shown in the right figure. The first part merely includes three aspects. The first is about an overview of code generation. The second is about the architectural description of Swift vector DSP processor. The third is about incompatible instruction selection. Select DAG is hardware-independent directed acyclic graph, which becomes machine DAG after instruction regularization and instruction selections and other steps. Machine DAG is hardware-related directed acyclic graph, which becomes machine instructions after instruction scheduling and finally becomes MC Einstein format of transmitting code after register allocation. Target architecture description include the description of register set and instruction set. Registers are merely divided into the following 5 classes: general register, vector general register, offset register, base address register, and modular register. I use the LLVM architecture description languages to describe the following information: register definition, register classification, coding conventions, and so on. Instruction sets are described in multiple levels of representation and definitions as shown in the figures below. Instruction class definitions are similar to object-oriented programming thinking. This is the architecture description class inheritance diagrams for the VMAX40 instruction. And this is the code that describes the architecture of the VMAX40 instruction. The backend needs to focus on dealing with incompatibilities between three instruction mappings. The first case is where an operation is not supported by the low-level IRs but is supported by the target instruction set. The processing method is instruction selections and painter machine, that is to find the combination of multiple low-level IRs instructions to represent the operation. The second case is when an operation is supported by low-level IRs but not supported by the target instruction set. The handling is done by leveraging the intrinsic function described earlier or pseudo instructions, where pseudo instructions means that the front end does not handle the instruction but the back end replaces the instruction with a combination of instructions in the target instruction set. The third case is when an operation is supported by the low-level IR and the target instruction set but with different bit widths. This is done by legalizing the operation described earlier, either by bit width expansion or truncations, or by simple declaring them unsupported. Finally, is about the evaluation and conclusion. I compare the factors of various target optimizations proposed in this PPT and handle optimizations on the compilation speed of the DLL models, and I take the performance value of hand optimization as the benchmark. Experimental results show that on-target optimizations can improve the performance of execution speed. I evaluate the whole compilation systems, including target optimization and code generation. Experimental results show that DLCS offers multi-slot parallel performance for target vector processor and achieves speed-ups ranging from 1.5 to 3 times over extending frameworks backed by handle optimized libraries. I present the designs of DLCS for the Swift vector DSP processors. DLCS learns the deep learning models to intermediate representation of two levels and realize the target hardware independence optimization and the target hardware dependence optimizations, so that the performance of the model finally deployed on the Swift vector DSP processor is far superior to that of hand optimizations. I hope that this work will encourage more research on DL compilation methods for self-development embedded chips and open up new opportunities for self-development embedded systems, hardware, and software co-design technologies.
Hello everyone, my name is Jinyu Liu. I'm currently pursuing the bachelor's degree in communication engineering at Dalian Polytechnic University. Today I'm going to present a paper titled An Accurate Frequency Estimation Algorithm by Using DFT and Cosine Windows. This is my catalog. The first part is the introduction. The next part is the proposed algorithm. The third part is the experimental results. The last part is the conclusion. The first part is introduction. Frequency estimation is the process of estimating the complex frequency components of a signal in the presence of noise, giving assumptions about the number of the components. Frequency estimation is a fundamental subject that has been widely studied and applied in wireless communication, signal processing, navigation, radar, sonar, assisted driving, and so on. Huge application areas vary from light spectrum estimation to direction of arrival information retrieval. Most of those applications require very fast and accurate estimation of the signal frequencies. Thus, it is necessary to have fast and accurate frequency estimation algorithms. It has just been mentioned that accuracy and algorithm complexity are the keys to judge whether the algorithm is good or not. In addition, the threshold at lower SNR and the performance at high SNR are also important factors to mushroom a frequency estimation algorithm. Well-known frequency estimation algorithms can be divided into two categories: the time demand estimation algorithm and the frequency demand estimation algorithm. The frequency demand estimation algorithms are mainly based on FFT and DTFT. This later does focus on estimating by using FFT and DTFT, where the time demand estimation is a varied problem. Figure 1 is DTFT and DFT spectrum of the complex exponential waveform with the frequency KL plus dirt. Being using rectangle and Hamming windows without noise. The Hamming window with its lower side lobes reduce the interference leakage at the cost mean lobe winding. It can be also seen that the convention around the peak changes significantly with the applied window. It can be seen from the figure 1 that the closer the calculated spectral line is to F, the greater the amplitude of the spectral line and the less suffer from noise. This part mainly describes an interpolation frequency estimation algorithm based on DFT and Cosine windows. The number of frequency sinusoidal signal in the background of additive white Gauss noise is Formula 1. After sampling, we have Formula 2. We perform n-point DFT on Xn, get Formula 3. K is the index value of the maximum spectrum lies. Cosine windows are widely used in many references. It is formula 5. Multiply Sn by cosine window, we have formula 6, where V equal L plus dirt is quoted the value of the signal frequency. L is the index value of the maximum spectrum line. Dirt denotes the normalized frequency offset. If it is assumed that the number of sampling points obtained is large enough and greater than 1, we have formula 8. In reference 4, the estimation formulas for the normalized frequency offset dirt, it is formula 11. When I equal 0.1, denoting the curly bracket as U and replacing the corresponding spectral lines in formula 11 by SWL, SWL plus 0.1 and SWL maximum 0.1, we have formula 12. Substituting formula 13, 14, and 15 into formula 12 to simplify the formula, we have formula 16. Substituting formula 17, 18, and 19 into formula 16 to simplify the formula, we have formula 20. The estimation expression of dirt can be obtained as formula 21. Through a series of complex operations, it is concluded that the proposed algorithm can be concluded by interpolation at position of the mean lowball and 0.1 of its left and right, and the final result is obtained. According to the algorithm tab on the right, we get the final estimated frequency. The performance of the proposed algorithm is high quality, and the influence of harmonic interference on frequency estimation results is effectively suppressed. In this part, in order to verify the performance of the proposed algorithm, we carry out simulation analysis in the process of harmonic interference and additive white Gaussian noise. Meanwhile, for the sake of finding the difference between the performance of the proposed algorithm and that of the competitive algorithm, expression 21 is the TED is used to describe the intensity of the influence signal. When n equal 128, SNR equal 50 dB, THD equal 5%. Figure 1 shows the MSE of dirt with respect to the signal frequency quotient value V of the proposed algorithm and MV-IPDTFT3 algorithm. Two iterations are carried out for both algorithms. It can be seen from Figure 1. When V greater than 5.5, the MSE of the proposed algorithm with two-term MSD window is the lowest. When V greater than 2.51 and less than 5.5 and dirt is close to 0.5, the MSE of the proposed algorithm with two-term MSD window is the lowest. When dirt is close to 0, the MSE of MV-IPDTFT3 algorithm with two-term MSD windows is the lowest. The change trend of Figure 2 and Figure 1 are basically consistent. It can also be seen from Figure 1 and Figure 2. Then for the same estimation algorithm, when h is smaller, the MSE is lower, and the estimation performance is better. Figure 3 shows the MSE of dirt with respect to the signal frequency quantization value V of the proposed algorithm and MV-IPDTFT2 algorithm. It can be seen from Figure 3. When V greater than 6, MSE of the proposed algorithm with two-term MSD window is the lowest. When V less than 6, in most cases, the MSE of MV-IPDTFT3 algorithm and the proposed algorithm with two-term MSD windows are lower than the other algorithms. The last part is conclusion. In this paper, an interpolation frequency estimation algorithm based on DFT and Cosine windows is proposed. It can be seen from the simulation results. The performance of the proposed algorithm is better than that of MV-IPDTFT3 algorithm, MV-IPDTFT2 algorithm, and Cosine algorithm. When V greater than 2.51 and less than 5.5 and dirt is close to 0.5, the MSE of the proposed algorithm with two-term MSD window is lower than MV-IPDTFT3 algorithm and Cosine algorithm. When V greater than 6, MSE of the proposed algorithm with two terms MSD window is lower than the competing algorithm. The proposed algorithm can actively suppress the effects of the harmonic interference signal. It can be used in complex applications with both additive white Gauss noise and harmonic interference. This is my reference. That's all for me. Thanks.